Hello, everybody. Welcome to today's live. If you have any questions, feel free to drop them in the chat. Otherwise, we're going to continue where we left off yesterday, talking about the different integral properties. So here, let me share my screen just to get started here. So just for a brief summary of kind of what we talked about yesterday. So yesterday, we kind of moved from the definite integral that we were talking about before, where we actually find the area under the curve, and we decided to start focusing on just the first part of that, which remember is finding the antiderivative. So remember, just a brief summary, what is an antiderivative? It's a function such that when you take the derivative of it, it equals the original function, right? So it's kind of like the derivative in reverse. And we were just kind of reasoning our way through a bunch of different examples and trying to notice patterns. So one of the big patterns that we picked up last time was the constant multiple rule for integrals. And then what we left off with was this assignment I gave to maybe give this a try. I give this a try before we come back. And here we want to basically see if there's a pattern here. So does anybody know, or was anybody able to figure out what the pattern is? Feel free to drop or to drop a comment in the chat as well if you kind of know or realize what the pattern is here. The pattern here is, as I create the new board for today, just a second. The pattern for this is that, I guess, how should I word it? The pattern here is that we're essentially adding one to the power and dividing by the new power. That's the rule. So here, and this is in general, like if you want to take the integral, this is what's called the anti-power rule, which we'll dive into today. If you want to take the integral of x to the n, basically you just add 1 to the power, so x to the n plus 1, so n plus 1, and then 1 over n plus 1. And of course, you also need the plus c. This right here is actually pretty powerful if you think about it. It allows you to take the integral or the antiderivative or the indefinite integral, however you want to word it, of any power, any just polynomial. So you could take the antiderivative of x to the 100th power just as easy as you can as x, or just as easy as you can with x squared. So that's kind of the idea. And if you notice, again, in the naming, we call this the anti-power rule, or that's what it's often called. It goes by other names. So you can say inverse power rule, I've sometimes heard, or power rule for integrals, however you want to word it. The bottom line is, you can kind of tell from the name, it is the opposite of the regular power rule for derivatives. And remember, that's kind of the idea. With each of these, and actually, let me grab what we were talking about yesterday. Yeah. So I want to come up with a kind of a list of different properties. I'll keep kicking them down a bit and kind of jumping to them down here. So looking at these, so if I just scroll down here, basically with these, or how should I say it, these constant multiple rule that we talked about yesterday, this would be like the next rule. So this rule, if I pull this down, is if you're taking this, then it's equal to, or this is the anti-power rule. So this, I'll do this in another line here. So this is the anti-power rule. So anti-power rule. And remember how the key theme that I wanted to get across starting yesterday was that every derivative rule that we learn is essentially the opposite of a rule we already know. That's the key insight. So this, as you might have guessed, is the opposite of the power rule. So what's the power rule? If you remember from derivatives, well, that's just if you have, some function, I'll say x to the n, so it could be x squared, x cubed, x to the millionth, whatever. Or it also works for negative powers too. That's the other benefit. But anyway, that's just equal to, if you remember, n times x to the n minus 1. So I would say for this first one, it's pretty clear that these two are opposites of one another, right? So like what we talked about yesterday with the constant multiple rule, if you multiply, so if you have a function times a constant and you want to take the derivative of it, well, that would just be equal to the constant multiple times the derivative of the function, right? So it's like that's what the normal rule is. Pull out the constant, take the derivative of what's left. So here the rule is the opposite of that. Take out the constant and take the integral or the antiderivative of what's left. That makes sense. This is a little trickier to see. Like, how is this process? So like, if you think about it, what are we really doing? We're multiplying by the power. So multiply by power. That's the first thing we're doing. And then we're subtracting 1 from power, right? And actually, yeah, I'll just say that as like a little note here. That's what we're doing for the regular power rule. What are we really doing, if you think about it, for the anti-power rule? We're doing the opposite of that. So we're and there's a good mantra that I recommend here when you're thinking about this. The key is opposite steps in the opposite order. So opposite steps in the opposite order. What does that mean? It means that basically instead of we don't start at the top, we start at the bottom. And then what's the opposite of that? Well, add 1 to the power, right? So that's the first step. If we swap the order, right, and then we do for each individual step, we do the opposite of it. We would add 1 to the power, and then what's the opposite of multiply? Divide by the power. So can you see that's what we're doing here, right? If the power over here is n, well, we're adding 1 to the power, or adding 1 to power, not from power. And then what are we doing after that? We're dividing by the power, like the new power, n plus 1. So the order matters. It matters whether you multiply or divide before you add or subtract. So hopefully, like this mantra, opposite steps in the opposite order, this is something you're going to see a lot. So this is just one example, but this is the anti-power rule. And you can use this to, like I said, take the integral now of basically any polynomial, like x squared, x cubed, x to the 400th power, x to the negative 400th, like 1 over x to the third. You can basically anything, I'll say. So there you go. Hopefully that makes sense. So that's one rule. That's the next rule, and then we'll talk about a couple of the easier rules today, probably, and then tomorrow we'll gradually over the next probably this week we'll get through all of the tougher rules. But this is going to be the week we focus on indefinite integrals. So hopefully that makes sense. Now the next thing that I would say, or how should we word this? Let's think about this. So think about what and actually, it's probably best if I just introduce the rule. Yeah, I'll just jump into it actually. So here, kind of like we had the constant multiple rule. Remember, we had this rule. Well, there's another rule that we know that's kind of similar to that, at least in terms of how complex it is. Not very complex. It's basically the sum rule, right? So the sum rule, if basically what the sum rule says, remember, is if you take the derivative of a function f of x. Remember, if you have two different functions, f of x and g of x, you can combine them by adding, right? And basically the rule is, how do you actually do that? How do you actually, like an example of this might be x squared plus sine of x. How would you actually take the derivative of this? Basically what you do is you do the opposite, or not the opposite, but you do basically the derivative of each individually and then add them afterwards. So instead of f of x plus g of x, the whole thing, derivative of the whole thing, you do f prime of x plus g prime of x. Take the derivative of each thing and then add them afterwards. Well, similarly, we have a sum rule for integrals. So we have a sum rule for integrals again, like not literally every single one of these rules, but like 95% of them, like the vast majority, have an opposite now, and that's what the integral rules are. That's why I said, remember, you don't really there's like 20, depending on how you count, 20 to 22 integral rules. You don't have to remember all of them if you know how to think about the ones you already have remembered, the derivative rules on the right backwards. But here, what is this really saying? It's basically take the derivative of each of them and then add them. So it's really swapping the order. Well, here, by the same logic, kind of, if you have f of x plus g of x and you want to take the integral of that whole thing, well, just take the integral of each individually and then add them. So that's the rule. It's again pretty natural. It's basically what you'd expect. So this is pretty powerful as well. So just to be clear, with these three rules, and again, there's like 22 total rules technically. With these three rules, you know how to take the integral of any polynomial if you think about it. So let's actually try that out before we go on. So let's actually think about if we had, let's say that we want to find the integral of, I'm making this up, 3x minus 4x squared plus 7x to the third. What would the integral of that be? Well, the first thing to notice, and this is another thing I should have mentioned, by the way, as well, when you see minus 4x, you can think of that as plus negative 4x, right? So in other words, the sum rule also works with the difference rule. Like if it was negative, that would be negative. So that you could argue there's also another rule called the difference rule, but it's really the same as the sum rule. It's just with negative numbers is how you can think about it. They're really the same thing. But anyway, it doesn't really matter. As long as you know how to think about it like that, we can just apply these rules one by one. So what does the sum rule allow us to do? Instead of finding the integral of this whole thing, the sum of these three terms, what if we just break it apart into 3x minus 4x squared and then 7x cubed, and then we find the integral of each. So the integral of the first one plus the integral of the second one plus the integral of the third one. What would that be? Well, and then here, what would we do next? This is where the constant multiple rule comes in, right? Because if you look at all of these, every single one of these is some function, like a polynomial or a monomial, x squared, x cubed, multiplied by a constant. So you can pull that constant out. You can pull out the 3 there. So 3 integral x dx. And then you can pull out a negative 4. So negative 4 integral x squared dx plus 7 integral x cubed dx. In other words, do you see how for every single one, we are pulling out a constant, right? We are literally pulling out a constant multiple. It was inside the function. We just pulled it to the outside. Again, you can only do that for constants, but for constants, you can and should do that. And now think about what we have left. The integral of x to the first power, right? That's basically x to the first power. How do we do that? Remember, we do the anti-power rule, right? So the anti-power rule that we just talked about, what do? You add 1 to the power and then divide. So add 1 to the power, x squared, and then divide. And then remember, we still have the 3 on the outside. Then minus 4 times x cubed over 3. Add 1 to the power, then divide. Then plus 7 x to the fourth over 4. And then we get something like this. So this will become 3 halves x squared minus 4 thirds x cubed plus 7 fourths x to the fourth plus c. So you can't forget the plus c as well. But this is the antiderivative, if you think about it, of what we started with. And if you're not sure about that, double check it, right? If we take the derivative of this, that's how you can always double check these. Take the derivative of this. What do we get? 3 halves x squared minus 4 thirds x cubed plus 7 fourths plus c. What would that be? Well, we drop the power down to the front and then subtract 1. So we get 2 times 3 halves x. So basically 3x checks out. And then hopefully I won't do every step, but you can see if we do the power rule here, we drop the 3 down. That cancels out with that. So actually I will do it. Minus 3 times 4 thirds x squared. 3's cancel. Minus 4x squared. Same thing. So drop the 4 out front. So 4 times 7 fourths times x cubed. 4 is simplified plus 7x cubed. And then the derivative of some constant c is 0. So when we do that, we get 3x minus 4x squared plus 7x cubed. So that's what we started with, 3x minus 4x squared plus 7x cubed. So that's what we get there. So hopefully that makes sense. And again, these are just, like I said, these are the starting rules. We'll talk about more complex rules as we go. But with these, you can actually do a lot, right? So with just these 3 rules, relatively, like the first 2 are kind of obvious, I'd say. They're kind of what you would guess. And then this one, it's not necessarily obvious. But it is, if you know how to think about it, right? Opposite steps in opposite order. It is the opposite of the rule you already know. So it's not too complicated. In the grand scheme of things, these are relatively straightforward. And with these, we can now systematically find the antiderivative of every single polynomial. So that's pretty powerful, actually. So with that, what we're going to do next time, I think we'll continue with this. So that what are all the types of functions that we know about, right? It's the antiderivatives of, or sorry, the types of functions are polynomials, trig functions, logs, and exponents. Those are really the 4 functions we know how to work with. We now know how to take we know the basic rules that we need to take the antiderivative of one of those 4 for basically any situation, or for literally any situation, I'll say. Any polynomial, you can now take the antiderivative of it with combining these rules. So we know that. There's 3 other ones, right? So we have the trig identities, We have or sorry, not trig identities, trig functions. We have the exponential functions and logarithmic functions. So now we need to do those. So what can we do exactly? We'll have to think about it. But basically, again, it's the same thing that we've seen, right? So like you already know how to take the derivative of all of those things, right? You know how to take the derivative of trig functions, the derivative of exponentials, the derivative of logarithms. So we're just going to kind of do those rules in reverse, and you'll see that. But next time, especially, we're going to pick up with the trig functions and how to reliably find the antiderivative of those, because it's kind of complicated, honestly. But we'll start covering that next time. So yeah, if does anyone have any last minute questions before we go? If you do, feel free to just drop them in Skool as well afterwards, and I can answer them. I can answer them there. But otherwise, hope that was helpful for everybody. Best of luck, and I will catch you tomorrow, same time.